Good morning, everyone. So before I start, I wanted to clear up one, I think, misconception from the conversation we had this morning. I know everyone wasn't there, but I think from the context of what I say, it'll be clear what we were discussing. Let's see, when I wrote my thesis, the code that I based my thesis research on, which is not what we were talking about, was in 1995. I wrote it in PVM, Parallel Virtual Machine. Some of you might remember that. Shortly thereafter, before I graduated, I converted to MPI, maybe in 97. From 97 until maybe 2020, so 23 years, I never changed the programming model. Even for multi-core, I just ran MPI processes on the different cores of a multi-core processor. And maybe some single processor optimizations no longer were necessary because compilers and hardware got better, but basically looked the same. So I really enjoyed that era, okay? People really liked that. No one wants to rewrite their code and eviscerate it and change it to a completely different programming model with completely different characteristics. The choice of the DOE, the choice the DOE made for the exascale machines is necessitated by really physics and the reality of the marketplace. Okay, so if you want to push the frontiers of capability computing past the sort of symbolic beacon of an exascale, which admittedly is arbitrary, but if you want to do that, you're either looking at 4,096-bit vectors, or you are going to have a power station sitting next to your supercomputer, or you were looking at GPUs because of their power performance. Okay, so I mean, there weren't a lot of credible choices, and so our philosophy then became, given that that's the reality of how we push the limits of capability computing, let's take a representative set of guinea pig applications, and it's not going to be one like we heard about from Lannel, and it's not going to be an entire user facilities worth of users, but it's going to be a large representative set, and let's do everything we can to lead the way. And so hopefully the people that come after won't have to do all of the hard work that we did, okay, in terms of maturing programming models, for example, understanding how to get the best performance out of the systems, building the sort of atoms that the applications are built on top of. There's just a lot of maturation that has to take place in the software. So that's kind of the philosophy. I'm not evangelizing a particular point of view. It really depends on what you're doing, right? But those were what went into the decision to go for that particular set of architectures. Okay, so that said, I'm going to talk about our experiences, and I'll take it from the top for people who aren't familiar. So the Exascale Computing Project started in 2016. 7-year, $1.8 billion does not include the hardware acquisition. Okay, this is everything else other than that. The hardware is purchased separately. And it is made up of 6 core DOE labs plus participation from 14 other labs, 48 universities, 12 companies, so just a lot of participants in the project. There are 3 main focus areas. Okay, there is sort of the enabling computational technology or the software. There is getting access to the machines and sort of help in leveraging and using the machines. And then there are all of the applications, so the domain-specific science that people are trying to get to run efficiently on these machines to do very specific things. So I'll talk a little bit about that. It amounts to about 81 research teams. Just to get a sense of how big each project is, there might be on average like 10 people per team, and it covers 9 different program offices in DOE, so it's a massive project with a lot of different participants. And I don't expect you to see what's back there, but I just want to sort of lay the groundwork for how it started. So the goal, of course, is to get this representative set of 24 domain-specific science applications running efficiently on this first-of-a-kind exascale systems. And projects range from things in material science, computational cosmology, astrophysics. There are energy generation systems, so fusion reactors, small modular nuclear reactors, particle accelerators, kind of everything you can imagine. I have sort of in the background a sense of the breadth of different mission-critical applications there in DOE. This is a subset that was chosen to be both representative of the science as well as the algorithmic motifs that we wanted to run efficiently on the machine. Okay, so we started with 24 application projects. That was 78 different codes. So obviously multiple codes per application project. Maybe there were 10 million lines of code. It's hard to count that, I know, but it just gives you a sense of scale. Some of these projects have large user communities, and that's obviously a huge obstacle because they're going to eviscerate their code base to get it to run efficiently on these new systems at the same time that they're supporting users doing a wide range of different scientific research problems. And all these codes were either MPI or MPI plus OpenMP when they started, with a few that might have used some acceleration from a single GPU on the Titan system at Oak Ridge. But it was basically just MPI and OpenMP codes when we started. And so here are the target machines. And every day I can say a little bit more about the Aurora machine, but this is the amount that I absolutely can say in the public. And I think the things to focus on for each machine, obviously the theoretical peak means less and less the harder it gets to achieve it, but we think of a sustained exaflop on the LinPack benchmark, which I know is dense linear algebra. It's not representative of a lot of what we do, but that's how the beacon is set. Number of nodes, I can't say the exact number, but of the order 10,000. And actually the node architectures are quite different. On the Frontier system, it's one AMD EPYC CPU, and there are really 8 GPUs. There are 4 pairs of what are called GCDs. They were shrunk a little bit to fit one on a chip, and they call the pair of them a GPU, but from the programmer's perspective, it's really 8 GPUs. So it's 8 GPUs and 1 CPU, and on the Aurora system, it's 2 Intel Sapphire Rapid CPUs in front of 6 Intel Ponte Vecchia GPUs, and I got permission to say just now that actually an early version of those chips is in the mail on the way to Argonne right now. So it's getting very, very real. And it's a fascinating architecture, a lot of risky and very innovative things. I don't know what I can and can't say. It's changing every day, so that's a different talk. HBM2 memory, slingshot interconnect, and you see the power numbers. And that's largely behind the choice of GPU accelerators, right? I mean, you cannot have a 200 megawatt supercomputer. It makes no sense. Already these numbers are beyond what I even thought would be tolerable when this project began in 2016. Okay, so there's obviously a ton to discuss there, but I just want to give you an overview. Our goal is these 2 machines. It doesn't mean there aren't many other classes of architectures that would be reasonable goals for different HPC projects, but to get to the beacon of an exascale, this is what our target is. Okay, so I want to talk about 4 parts of what I experience the application development projects doing. It's so different from what you would normally think of as just porting. And I think of there being sort of 4 components to it. The first is every application that's part of this has to demonstrate a scientific use case that is considered valuable in their community. So you have to say, this is why I want the capability of an exaflop, or whatever measure beyond what the scale of what they're doing right now. And that has to be vetted and reviewed, and it has to be significant. Without that, it's sort of pointless, right? Then there is all of the algorithmic innovation that goes on. Some of the algorithmic innovation over the period of 7 years is completely independent of the hardware. Some of it could just be reduction in operation count, so faster convergence or fewer operations, or reducing the complexity, either via some kind of reasonable approximation, or it might be just a smarter algorithm. Doesn't necessarily have anything to do with the GPU. But then there's another class of optimizations that target the particular features of GPUs. It's kind of hard to disentangle them sometimes. I consider one purely algorithmic and the other kind of porting. But porting doesn't almost ever just look like rearranging some loops and laying out memory differently and exposing some more axes of parallelism to get it to run faster on the GPU. It's much, much deeper than that. And it touches many aspects from all the way up from the physical model all the way down to how the data is represented and everything in between. So I think it's important to realize that. And then integration, you have to be so specialized if you want to even fool yourself into thinking you understand what the hardware is doing, that at the level of a domain scientist, it becomes more and more common to depend on other people, okay? And so integration is in allowing people with different expertise either build custom libraries for the motifs that your code is built around, or to use their expertise on your code team, or it can mean a lot of different things, but it's about not trying to do everything yourself, and that's why there are these other components of the project. Okay, so I've read Hennessy and Patterson many times over a long time, and I noticed in the newest version of the book they had a quote that I thought captured really well, when they talked about benchmarks, because I want to be very clear that we're not doing a benchmarking exercise. So if you're doing a benchmarking exercise, it has to be a little like LinPack, where you say, well, here are the rules, and I want to really see what the hardware can do. So I want to limit the innovation on the software side to make sure that you're not cheating and you don't get a good LinPack score because you found a way to skip some operations or something. So we're very much not doing that. And although that's appealing if you wanted to do a direct hardware comparison, it really stifles innovation. Okay, so they said, if you did that, one system, if you do what we're doing, you couldn't disentangle the two. One system could win because of, say, the algorithm and not because of the hardware or the compiler. And while these guidelines are understandable when the foundations of computing are relatively stable, as they were in the 90s and the first half of this decade, they're undesirable during a programming revolution. For the revolution to succeed, we need to encourage innovations at all levels. Okay, so that's very much the approach that we have adopted, and it means you will see speed-ups that wouldn't make sense if you think of a benchmark hardware comparison, because at some point you just really can't make a direct comparison anymore because you've changed things so much. So it's important to realize that, and you wouldn't want to do it any other way. Okay, so here is kind of my high-level view of the phases of the project that people have gone through from 2016 till now. So and this is all assumed to be on massive networks of these things. And that actually makes a big difference. Everyone thinks, well, the MPI problem's solved. Everything is just about scaling in and getting fine-grained parallelism to perform better on a node. But it's actually not quite true. But anyhow, if we forget about that and just start with many-core CPU, then CPU plus GPU around the time of the Titan system at Oak Ridge, maybe that was 2014 or something. Then going from CPU to multi-GPU actually is a bit of a leap. Okay, it's not without its issues. And then there was this big move to what we call GPU resonant algorithms, because as the GPUs accounted for more and more of the performance of a node, it went from 50% to 70% to 90% to now 97% or so. The cost of moving data between the CPU and the GPU became a bigger and bigger bottleneck, right? And so in order to not have to pay that cost, people thought more and more not about taking a special loop or two and running them on an accelerator, but instead parking everything in the GPU memory for as long as you possibly can get away with it. And that just takes a lot of rethinking how you do things, right? But anyhow, that was, I consider, to be like a phase everybody went through. Then diverse multi-GPU was a huge deal. So we went from the only player in this field for scientific computing was NVIDIA. And whether you like CUDA or you don't like CUDA, the compilers are relatively mature. The performance analysis tools are relatively mature. There's the ecosystem of software around, that's provided, whether it's solvers or, and pretty much anything that you typically need, just the runtime system, is very mature. And then we went to, as you saw on the slide I presented earlier, AMD GPUs and NVIDIA GPUs. And these are not trivial differences, okay? Because it takes a long time to get to that level of maturity that we were accustomed to with NVIDIA. And then so we're sort of at the stage now in the project where we're focused very much on architecture-specific optimizations to meet our performance goals. And you might never want to get to that last point yourself, but again, I think of this as sort of leading the way. In terms of programming models, and I sort of I was at the beach one day and I thought, I drew this on a piece of paper and it looked good, and then I tried to render it in PowerPoint, and it makes me look kind of crazy. But I think the idea is pretty obvious, which is that there's a trade-off between how much control the programmer has over the performance and how much productivity in the form, typically, of portability the code has. And unlike what we're used to from a long time, there's a zoo of options. Everybody's kind of thrown their hat in the ring to produce a programming model that finds the optimal point in this two-dimensional space, right? So I'm going to show you what our distribution of programming model choices looks like, but it's evolving really fast, and people are jumping ship on some things and adopting other things, and it's kind of interesting to see how things coalesce and how dynamic it is and how quickly it happens. So anyhow, on the bottom right is sort of CUDA, HIP, and SICL. So those are what you think of as, at least in the sort of GPU world, the vendor-specific model for getting performance on the GPU. And then all the way in the upper left are what we think of as motif-based. They're not really libraries exactly because they're built a little bit more custom with the application, but it might be adaptive mesh refinement library, or it might be finite element library. Things that really insulate you from all those details and that come to the application level. Then there's just a lot of options in between. So here's how things break down in ECP. For all the codes, I listed 78, so it should come close to 78, maybe 76. I drew arrows where we've had kind of migration. So there's always been this discussion of Fortran and C or C++. A lot of it, honestly, doesn't even come down to the properties of the language. It's just the reality of what's most mature first. And people start to get nervous that Fortran is not going to be supported early enough in the software releases for the machine. And like, say, the OpenMP compiler might support C++ much better than it does Fortran. Fortran might be more of an afterthought. And so it kind of creates this reality. And there are obviously other reasons. I'm not really interested in debating it, but we've seen a big migration from Fortran to C and C++ during the project. It went from about a third to now, whatever 14 divided by 64 is. And in terms of programming models, it's still pretty widely distributed. OpenMP, maybe 5 or 6 of the projects are deeply invested in OpenMP. So if you don't know, the traditional OpenMP that you use to run on multi-core processors then developed into OpenMP offload, which also can allow you to use markup it's basically directives that allow your code to be, to execute on an accelerator. And that's a work in progress, right? And so it's actually like, from the inside, it looks like a major co-design effort between the LLVM developers, the compiler developers in Intel and at AMD, and the people who are actually using it to try to get performance on their code. Okay, so anyhow, I want to talk about some where we sort of are and what I see as some of the major challenges, what has been easy and what has been hard. So I'm going to explain at a big picture why it's such a big challenge. One is that these are not fixed problems that people are solving. Over a 7-year period, people are doing a lot of research. Okay, and in the course of doing that research, they take left turns and there are new opportunities, new algorithms are developed and published. So there's sort of this inherent zigzagging that goes on over something that's as protracted as this project. Obviously, GPUs have their best fit computational motifs. Okay, they're general purpose processors in a sense, but they obviously do very well with things that are SIMD-izable and that have a ton of fine-grained parallelism. Okay, and that I'll talk about more about that in a second. The time for maturation is significant when you have new compilers and when you have new libraries. And there are significant dependencies, as I said, on other aspects of the project. So a lot of people these days don't build everything themselves, and to coordinate all of those dependencies is really difficult in a project sense. So we know, just as a precursor to what I said, I won't go through these things in depth, but I just sort of brainstormed, what is easy to do on a GPU. And if you don't fit into a reasonable number of these things, then you're going to have to start thinking a little bit more deeply about how to recast your algorithm in such a way that it can take advantage of some of the natural properties of a GPU. So some of these are the same for CPUs, some are unique. And one of the things that we've had a lot of trouble with, as I mentioned earlier today, is strong scaling problems. Okay, and strong scaling problems are difficult just because if you have a fixed problem size, you increase the number of GPUs, then the problem size per GPU is smaller, and a GPU depends on exactly the opposite to be able to achieve near peak of its theoretical performance. You need to really oversubscribe it, right? So what looks really good on one GPU might not run very well on a big cluster of GPUs. So what people typically do is they make the problem more complex. So they use this as an opportunity to either refine the physics or add more particles or add more models or include some kind of optimization loop or something such that you're doing a bigger problem at the same speed versus the same problem now not being able to speed it up. And that's actually better on CPUs than GPUs. And the value that sort of threshold local problem size value traditionally was called n sub 1/2. People call it n sub 0.8 these days, but it's just a representative value of the problem size. So anyhow, that said, one thing we do is we track the ratio of the performance now on the fastest system that exists. And we have the Summit supercomputer at Oak Ridge, which is 200 petaflops, which is built off of NVIDIA Volta's 4 per node. And there are 5,000 of them or so. So all of the codes in ECP were optimized for and tested on Summit, and we measured all these values. And I put a value of 50 because that's sort of the bar that we have to get over. There's a huge story within each of these, but I just wanted to show you the range. That's really what I want to say. So I showed over the course of 2019 to 21 the progress that's made on these figures of merit. These are application-specific ways of determining performance. So it could be particles per second or grid updates per second or whatever makes sense for it, or something more complex. There might be a complexity term, depending on the algorithm. So there's a huge range. And I want to talk about some of the lower ones and some that don't even appear here because we don't hold all of our codes to this particular standard. If people are doing very new things for which there was no baseline to compare to, then we don't try to pretend like we can make that comparison. So I want to talk about some of those. And I'll do it under the sort of general topic that HPC computational motifs and use cases really are expanding compared to what I've seen, in the past 20 years or so. And a lot of them are expanding in directions that are very hard to get performance on this class of systems. And I'll tell you what some of the underlying motifs are and why. Distributed hash tables, a lot more graph analytics problems, things like sequence alignment for doing metagenomics. It's always been a lot of sparse matrix stuff, but it's not so easy to get good performance on sparse matrix operations on GPUs. We heard about that earlier this morning. So the more that you find yourself in this corner, the more difficult it is, and the more you have to deeply think about how you're going to change what you're doing if your goal is to get performance on these systems. And you have to remember that's the mentality, right? The mentality is the physics in the marketplace determine these systems. Once we decided we wanted to stand up exascale machines, we have 24 teams. Do everything you can to lead the way to get performance on these systems. And if you do that and you find yourself in this area where there are a lot of new applications that people are working on, it's amazing the amount of work you have to do and how fundamental the rethinking has to be in order to get performance. So I'll just mention a couple of examples before I run out of time. One is metagenomics, which I mentioned. This is Kathy Yellick at Berkeley. And if you're not familiar with the metagenomics problem, it's kind of fascinating. You scoop some dirt, or you get a bucket of lake water, or you get some bark off a tree, and you want to infer what the microbial community is by doing DNA sequencing. So it's kind of like you've got a bunch of pieces to 100 different puzzles, and you've got to put them all together, maybe with some missing pieces or some torn pieces as best you can. And the pieces of the puzzle are these initial reads you get from a DNA sequencer. And then from those, you build these things called contigs. The point is, when you put it all together, there are all the motifs are things that HPC systems were not traditionally optimized for. Okay, so you have something called de Boering graphs, where you have to do searches on de Boering graphs. You have, when you find something, you have to use distributed hash tables. The alignment algorithms and a lot of sparse linear algebra are all huge challenges. So if you were just going to buy a machine to do this problem, you probably wouldn't run and buy a GPU. Now if someone said, do everything you can to get something like this to run efficiently on a GPU, it becomes very interesting. Okay, so they published some really interesting papers recently. This is one, so when you look from left to right, these are performance comparisons, higher is better, of the number of updates per second they get using, on the left, 2 GPUs, 4 GPUs, then 8 GPUs versus a 32-core CPU. And I would say it's comparable if you were to do a fair comparison. The reason they're using 2, 4, and 6 GPUs is or 8 GPUs is because that's how many there are on a node at the supercomputing center at LBL, at NERSC. I have the paper linked here, but the way you have to fundamentally rethink the problem to be able to match or slightly exceed CPU performance is really fascinating. So since then, they've kept pushing it forward, right? And I think it's an open question. And that's for sequencing on the right is for protein clustering. So you don't just want to sequence the metagenome, you also want to find clusters of proteins that have similar behavior and infer what it is that they actually do. And then you actually want to track these things dynamically over time. So when you look at the actual full application, though, what I showed you in that previous chart is just the part that the arrow is directed from. So the overall application doesn't speed up that much, even if you're able to non-trivially speed up that one Smith-Waterman kernel. Okay, that was the performance of Smith-Waterman. So they have a paper on how they tried to optimize it for a GPU. So it's difficult, and it's an ongoing research project, and it's not nearly as easy as doing the n-body problem or many of the other ones where you saw the performance way beyond the threshold of 50 that we were hoping for. Another one is doing X-ray diffraction patterns. So we have these massive light sources, one which is incomparable in terms of the short duration of the pulses, and the brilliance is at the SLAC facility is called LCLS, the line coherent light source at SLAC, and it's used to image complex molecules, right? And so you shoot these X-ray pulses at these streams of particles, and you get diffraction patterns. And it becomes a really interesting, complicated computing problem to take the 2D diffraction patterns and be able to produce a 3D image of the molecular structure. There are a number of steps to it, which I'll show you on the next page. But the workflow looks quite different from typical HPC workflows. So you're streaming data, and ideally you'd be able to do this in real time. It's very expensive to get beam time, right? So as you learn about what you're seeing, you might even use it to adjust the laser or make other real-time decisions. So there are certain performance thresholds people want to meet, but the underlying performance bottleneck is non-uniform FFTs and sort of like an optimization loop where you're comparing the model parameters with the measured parameters, and you're trying to find the best fit between them in order to infer the structure of the molecule. So these are not typically what you'd think of as automatically running well on a GPU. And so I just had one example here where I show the merging, the orientation matching, and the slicing. Those three pieces were ported to a GPU with a lot of work and a lot of interesting ideas. And they were able to get a factor of 2 speed up or so. Wrote an interesting paper on it. I guess I should have put it in the talk. But I guess the bottom line is that it doesn't come for free. It's a lot of thinking. So a lot of the work was done in the non-uniform FFT kernel, but it's a lot of rethinking how things are fundamentally done to get to that point. So still, not easy. Another one is the huge optimization problem, which is modeling the dynamic behavior, particularly under failure scenarios of the power grid. Okay, so this can be represented as a massive optimization problem, and I won't go into too much detail because I'm running out of time, but I'll just say that it has to be completely rethought how to be able to do this problem efficiently on GPUs. So it's a massive nonlinear optimization problem with large, sparse, indefinite linear systems. There are no good sparse, indefinite linear solvers for GPUs. They don't perform as well as the ones on CPUs. So they decided to take a totally different approach and use the decomposition to create compressed dense systems, increase the number of floating point operations you have to do. Obviously you can't read the slide, but you can see the sparsity pattern on the left turns into the density pattern on the right, which is then done very efficiently, at a significant fraction of peak on a GPU. But it turns out that the number of floating point operations scales horribly with system size for the densification problem, as you see on the blue line, and therefore it's just not feasible. So they did a survey of all the possible sparse indefinite solvers on GPUs compared to their reference CPU solution. Nothing was really able to beat it yet. So it's an ongoing research project, and they're able to maybe tie it or something. And the last one is small modular reactor design. I'll just say a couple things about this. So this is really fascinating how this problem had to be completely redone. Why? Well, they use Monte Carlo techniques. So Monte Carlo is very general. Every single neutron is tracked independently of every single other neutron through a series of interactions which are determined by sampling from complex probability distribution functions. What's the problem with that? If you parallelize over neutrons, they're not SIMD-izable. Everyone is doing its own thing, right? Totally independent from each other. So you get horrible branch divergence on a GPU and very poor performance. That's the classic history method. It works quite well on a CPU, right? So on a GPU, they had to totally rethink the problem and change from what is known as a history-based method to an event-based method. You're really kind of inverting the whole algorithm. So I'd be sympathetic if you had constraints that this would be a very difficult software change, because instead of doing each particle independently, they sort the particles after each step in terms of common interactions. And everyone that's undergoing the same interaction gets processed as a vector, right? And so it's a big sorting problem, and once you sort, you can cut up into warps, as they say on GPUs, these common operations. And eventually they got fantastic performance on the GPU. Okay, so they were able, I think they're 3 to 4 times faster than a highly optimized code on a CPU. But it didn't come for free, is my point. It was a lot of work for these non-standard classes of algorithms. So I'm trying to show both sides of it. Okay, there's not a simple answer. And so I'll summarize with some final thoughts. First, it's very hard to push the frontiers alone these days. Broad collaborations of diverse teams are really what have allowed us to get as far as we have. So of these 10 people that I referred to, almost always led by a domain scientist who, in most cases, doesn't know, can't even really talk that much about the hardware, let alone really understands it. And mixed in are applied mathematicians and then people who work more at the hardware-software interface. Much broader adoption of enabling computational tools than I've seen historically in the 25 years I've been working in this area. And a lot of code-designed application-level libraries are much more common than they used to be. Also, hardware and programming models drive methods, models, and algorithms as much as the reverse. Okay, so once you've said, I'm all in on this particular class of architectures, people really are clever. People are really, really clever. Doesn't mean that's the right thing to do. I mean, it really depends on a lot of parameters that that are specific to every project. But if you do, people are really smart. And they can find ways to get it to work, given the time and given the resources. In other cases, it's just really simple. It's just a very natural fit for the GPU. But anyhow, I found that very interesting. And also, this project is much less about porting in benchmarks than it might appear from the outside. And it's really supporting innovation at all levels with a very subtle interplay among them. And that's really what's key to progress. So you don't want to put any constraints on anybody to do the most creative thing they possibly can, even if it hurts your ability to quantify their success in some way. And the last thing is, I think I really underestimated how long it takes software to mature on new systems. It just takes everybody all in for years and years hammering on things to get them to work to a level that you might take for granted if you're used to working on mature systems. And I think our goal is, through this project, to kind of lead the way. So when other people come along and might want to use this class of systems, it'd be silly to say this is the class of system. It just totally depends on what you want to do. But it is a very viable class of systems that it'll look a lot easier. You have a much better version of, say, OpenMP, and there might be programming models that insulate you from having to specify whether you're running on a GPU or a CPU. In fact, we have those already, but they might look much better. So anyhow, that's the goal, and that's kind of the way I see things. And thanks for your time, and I'll take any questions.